Hi everyone, so I wanted to go through number 6 with you on the IB proof practice packet. This was our mathematical induction problem. Now before we get into that, I actually want to go over one small thing. So when we're working with mathematical induction, specifically with summations, we are given the pattern right off the bat and we're trying to prove that that pattern is correct. Now, not every summation is going to have a special pattern to it. If you remember at the beginning of our lesson on mathematical induction, we were given a problem that said, what's the pattern? And we were given the summation, and we needed to figure out what that pattern would be. So I already have it pre-written for us. The first term in my sequence, my sum of the first term, is going to be 1/2, and this will probably look familiar to you as we get into it. My sum of the two terms is my first term plus my second term. When I add these together, I end up getting 2/3. Now these came from plugging our numbers in to the summation, so I know that I'm going to stop at 2, stop at 3, stop at 4, and continue. My sum of the first 3 terms is going to be 3/4, and then my sum of the first 4 terms is 4/5. So maybe you're noticing a pattern right off the bat. My numerator is exactly the same as my term number. Got rid of that accidentally. And then my denominator is my term number plus 1. Now this is only going to work for my positive integers. So that's going to be starting at n equals 1. So that's just a quick summary of rules for summations. Now when we're working with mathematical induction, we will be given this and we will say, prove that this is true. So it will be given to you right off the bat. You will not need to figure out what that rule is. So jumping into the first problem, the problem number 6 in your packet comes from the May 2023 exam. This is a non-calculator exam. This is paper 1. So we want to use mathematical induction to prove that this is true. So just a quick reminder, the left-hand side of this equation allows us to figure out what each individual term is and add those terms together. My right-hand side of the equation allows me to figure out what the pattern is. So this is my right-hand side of my induction equation, and this is my, left-hand side of the equation. We know that when we're working with mathematical induction, the first thing we need to prove is the base case. I forgot a very important step here, and that's just noting that n is an integer. So n is an integer for n is greater than or equal to 1. So I'm going to state what my supposition is. So I'm going to say P of n is, you can just rewrite the problem. I can say P of n is this, rewrite the problem, but we always need to state that. Now for my base case, I want to say that if n is equal to 1, I'm choosing n equals 1 because I know n is greater than or equal to 1, so n is the smallest number that I can possibly plug in. So if n equals 1, my left-hand side is going to look like this. R equals 1, I'm stopping at 1, R, and then R plus 1 factorial. So this is going to simplify down to 1 over 1 plus 1 factorial, 1 over 2 factorial, which is just 1 over 2. So this is what my left-hand side of the equation is. My right-hand side of the equation, I'm plugging in 1 for n. So I have 1 minus 1 over 1 plus 1 factorial. So I have 1 minus 1/2, which is also 1/2. So this tells us that P of 1 is true. Remember, if this is false, your proof stops here. You do not need to keep going. But if your base case is true, you can move on to step 2. For step 2, we are going to assume that P of K is true. So this tells us that this is true. And all I'm doing is rewriting P of N, but with K. That's all I'm doing. That's it. So I assume that this is true. Now for step 3, I need to prove P of K plus 1 is true when P of K is true. You may not need to write this step down. I'm just writing this just so we know where we are going. Now again, the left-hand side of my equation is my summation. That allows me to list out all of my terms and add them together. My right-hand side gives me the pattern that this follows. So if I want to represent P of K plus 1, I can rewrite this as K R equals 1, R plus 1, factorial. And then I can say plus K plus 1 over K plus 1 plus 1 factorial. So again, my left-hand side gives me the sum of the first K terms. Now, I don't want to adjust my summation because I don't have any information about K plus 1. I only have information about K. So I'm going to use what I'm given in step 2. So I can say that 1 minus 1 over K plus 1 factorial. I know that these two are equivalent. Now, you know from Algebra 1, if you add something to one side of the equation, you better add it to the other. So I'm going to add K plus 1 over K plus 1 factorial to the other side. This is allowing me to keep my equation balanced. If I add something to one side, I need to add the exact same thing to the other side. Now, if I were to combine this, I could say that this is equal to K plus 1, R equals 1, R plus 1 factorial. I'm trying to prove that my left-hand side or my right-hand side is going to equal my left-hand side. Prove that P of K plus 1 is true when P of K is true. So my goal, what I want to happen is to show that this is true. This is my goal, try to show that this is true. So I'm going to manipulate this side of the equation to get it to look like this. Now I'm going to erase everything that I just wrote because that's actually, I don't know that yet. That's what I'm trying to prove. Now, the first thing that I'm going to do is I'm going to distribute my -1 into the first term. So I'm going to rewrite this as plus 1 over K plus 1 factorial. And you'll see where I'm going with this, so just bear with me right now. And I'm going to change my denominator to K plus 2 factorial. All right, now I'm trying to prove that K plus 1 is true with the summation and with the right-hand side of the equation. And I know that in P of K, I have 1 minus something. So I'm going to try and get my right-hand side of the equation to look like that. So 1 minus something. I'm going to try and rework this side of the equation. So I'm going to have my 1 all by itself. I'm going to get a common denominator here. So I'm going to multiply my first term by K plus 2 factorial. And then my second term is going to be multiplied by K plus 1 factorial. So now my denominator becomes K plus 1 factorial times K plus 2 factorial. Just a side note about factorials. I know that 3 factorial is equal to 3 times 2 times 1. I also know that 4 factorial is equal to 4 times 3 times 2 times 1. Now, if you notice, we have these numbers in common. So I can rewrite 4 factorial as 4 times 3 factorial. So you can take your current term and subtract 1. So I'm going to use that same method with this k plus 2 factorial. Just to give you a little sense for where I'm going. I know that in my original problem, my goal is to get just a k plus 2 factorial in the denominator. So I need to get rid of this term right here. If I manipulate this to say k plus 1, I can factor out a k plus 1 for my numerator and cancel that with my denominator. So I'm going to change my numerator to say negative k plus 1 factorial times k plus 2, and then the rest of the equation is staying the same. Now I'm going to factor out my k plus 1 factorial. I'm left with negative k plus 2 plus k plus 1. Then my denominator is still the same. And now I can go ahead and cancel these two terms out. So I'm left with 1 plus, I'm going to distribute this negative while I'm here, negative k minus 2 plus k plus 1 all over k plus 2 factorial. My k's are also going to cancel, and I'm left with 1 plus negative 1 over k plus 2 factorial, which, if I want to be fancy, I can rewrite as 1 minus 1 over k plus 1 factorial, which is proving what I was trying to prove. I was trying to prove that if I use k plus 1, it would still be in that same format. I did prove that. It still has the same pattern, even if I use k plus 1. Now I'm not finished. We need to write our final closing statement. So we can say if p of 1 is true and p of k plus 1 is true when p of k is true, then p of n is true for some integer n where n is greater than or equal to 1. So this sentence you will have written every single time you are working with a mathematical induction problem. The only two things that will change are your domain and your base case. So if this number is 0, this better say 0 right here. So make sure it matches. But that is my closing statement, and I have finished with this mathematical induction problem.